All right, you guys have already talked out in your groups trying to narrow down some of the questions for me. We're about to grade evens, and some people said it got weird around 27. And then some people said just number 7. But number 7 was an odd. Let's check the even. Number 14. Geoseries R is equal to 5/4. Hey, what lets me know that it diverges? Geoseries are technically, could an nth term, kind of? Because the limit would be infinity. But I know. That's a little bit rough. So geoseries, yeah, totally diverges. Number 44. Number 44. I know it skips over the derivatives and integration part. I know that we might have some questions on that, but were you able to take that repeating decimal and write it out as a geoseries and see that the common ratio was just a 1/10 every time because you're just budging another decimal place every time? AKA, the series converges, and were you able to get the decimal that converges to? Hey, is that a practical question in some way, shape, or form? Do you always have decimals more than fractions? Not a big deal? Okay. With mental math, I'd much rather have a fraction than a decimal. It's interesting that you didn't write out any repeating decimal just by making it an infinite geometric series. I think it's interesting, but maybe not. I mean, 0.33333 is an easy one. 0.111, what's that? 19. No one else knew what 0.111 was? Okay, 2 people did. No one else knew? No. How about 0.16.1? Oh, 0.16161616. What's that one? No, that's the 1/6.
Wait, how do you do that?
Long story short, are there repeating decimals out there that some of you don't know? Yes. Could you use your calculator? Yes. Could you just do an infinite geometric series?
How do you just know that? You just memorize 0.01 that has some.
For the rest of you without Lorenzo's brain where repeating decimals are stuck in his head, could you just use this process to basically find any fractional equivalent of a repeating decimal? Yes. Interesting. Huh. I wonder how a calculator goes from a decimal to a fraction. Anyway, number 56.
Oh.
Number 56. Assuming. Did you guys figure out that your common ratio was x cubed? You can make the function of, or from the function a is equal to 1 minus r. You have your power series, and then you would have plugged your x cubed into your interval, but it's still negative 1 to 1, just like x squared, which is kind of boring. 68 is c and 70 is d.
Write out the series. Can we just put a sigma?
You could have written a sigma. I don't know what the directions were. Some of them said write the first 4 terms in the general term. So if on the AP, PS, that does show up on the AP for writing out a series and the general term. They love making you write the general term.
So
you need to write it out or else you won't get those points. But
you cannot write a sigma.
If they ask you to write out the first so many terms in the general term,
no,
a sigma would not be efficient.
Not the first terms. That's to find a geoseries.
Oh, if you, that's all it said. Yeah, Lorenzo, I was just trying to say if the exact wording is there you needed to, but if not, a sigma's fine. A sigma's fine. 68 is C, 70 is E, and I think with that we're done. If you were writing the sigma, it just depends on if you're the one writing it. What was that? 56? If you're the one writing it, yours, you just have to make it match. Because Lorenzo was saying, could you write a sigma? They weren't actually expecting you to write a sigma, but you could have. But if you did, I mean, you must start at 3 because that is your initial term. So it must go 3 and then 3x cubed and then 3x to the 6, etc. Right? And so if that's true, you just need to start at 3. So if you need to start at 3. And if you did 3 times x cubed to the, right, what are you going to make it? Well, if you have it starting at 0, well then that's fine, just make it n, because then when you plug in 0, everything is 1, 1 times 3 is 3. But if you put in n minus 1, you must start at 1 to have it match. Does that make sense? Just make it appropriate, if you're making a sigma, which you are in this case, and you didn't even need to, so that's why it's optional. Okay, guys, but I'm not even pretending that that covers all the homework questions, but I'm hoping you at least got a few narrowed down. Those of you that are still stuck, those groups that are still stuck, where are we stuck? 25. 29 builds on 23. We don't like the ones going with 23. So let's go ahead and peek at 23 really fast, just because we're going to have to start there for all the other ones, right? So number 23 is in 29, is in 33, and then we can talk about 25 real fast. Actually, let's talk about 25 first, because he's unique. The rest of them build on 23. So number 25, the directions are... Wait, what does that mean if it's finding the values of x for which the series converges? What's another... Yeah, basically an interval of convergence, or what values of x it works for. Now, this is a super interesting one, because this one has a sign in it. Yeah, and we didn't see anything with sign yesterday as far as in the geoseries. But do you see how sign is being raised to the n? Okay, to the 0 power, and then if you wrote it out. So my common ratio needs to be less than 1, but what is my common ratio in this example? But what's interesting about sign being in between 1 and negative 1? It is already in between except for... Oh, so wait, this is always true for all real numbers except for... Can't be pi over 2 or 3 pi over 2. I need to add a pi in, so I skip from this quadrant, 180 down to the next quadrant, etc., etc., etc. I can't just say pi over 2n, but I can say pi over 2 plus pi n. Because basically, I just can't have sign be 1 or negative 1 in order for this to work. But this is our first introduction to, wait a minute, hold on, is it possible for some of these to always converge? Like, as you keep writing it, it'll keep getting closer and closer and closer to the whole thing? Interesting. But, AJ, we were just still using that geo series about the interval of convergence says whoever the ratio is less than 1. And so this time, the ratio was just sign. What was interesting is sign is always in between 1 and negative 1. Remember our little wave? Oh, but it is 1. Can't be that. Oh, it is negative 1. Oh, can't be that. But then all the rest of them that you said just a second ago built on 23. Now, I think you got 23. You were asking about the future ones, right? Yeah. So hold on. Let's start with 23 and then use it to find 29. Guys, you have the directions. It wants us to find what?
29.
Find f prime. And then in 33, it wants us to find the integral. So, first of all, let's talk about the power series. The power series. So, guys, what was the power series you got for 23? What is the series itself?
Negative x plus 3 over 2 to the
Plus 3? You mean negative x minus 3? No? Okay. So as we have the power series, then in number 23, you could have gone ahead and made that into a function. What would the function have been?
2 over x minus 1.
I was hoping that for the kiddos that are needing to actually understand what's going on, that we wouldn't be jumping to the final simplified answer, but we'd be writing this. So 1 over what?
1 plus x minus 3 over minus 3.
Which ends up making, yeah, minus and negative would be a plus, and then we could go ahead and get a common denominator, and then move that to the top, so we would have 2 over 2 plus x minus 3, which, yes, we could go ahead and simplify and make it instead 2 over x minus 1, right? Let me know if I'm wrong. Are we good? Okay. So that's number 23. So let's use that. So what does number 27 say to do? Okay. Now that we know what this function is, when number 27 says to find f prime, couldn't we find f prime just by taking the derivative? Sure? Okay. But that's not what they want. They want the power series equivalent. Now hold on. If we were making a power series, wouldn't we need it to match this again? Do we want to make that match back? Not if I already have a power series with this one. So how do I go from having a power series of this one to having a power series of the other one? Take the derivative piece by piece. What's the derivative of 1? 0. So in order to find this derivative, I'm just going to say, oh, sweet, I'll just derive his power series. It's a polynomial in some ways. I can just go ahead and go for it. So derivative of 1 is 0. Derivative of this one, bring down the 1, it'd be negative 1/2, right? Derive this one, bring down the 2, that's 2 over 4, which is 1/2 times. I would bring down, wait, that would be the third power that time, right? It'd be 3 over 8. Does that make sense? To derive f, to derive the function, we derive its power series, just term by term. So then how do I do number 33 where it says instead of deriving, let's integrate? Wouldn't that be 2 ln of x minus 1? You want to make that match that? I haven't talked about interval convergence. Are they asking about it?
Yeah.
Okay. We'll get back to interval convergence. I'm just trying to make sure that those with the questions knew what to do. Oh, I didn't know that they wrote it down. Okay, I thought they just had to integrate. So 0 to x. Which I would rather that be more like a t, dt, but oh well. So when I anti-derive, we plug in the x and then minus plug in the 0. But plugging in 0 with fundamental theorem of calculus would be the absolute value of 1. ln of 1 is 0, so it doesn't matter, it goes away. So we just end up with this, right? And then how do I integrate this term by term? What's the integral of 1? X. The same way I derive to get f prime, I'm going to integrate to get the integral from 0 to x. Integrating the next one, I would go ahead and up the power, right? And I would have x minus 3 quantities squared, but then I'd have over 2, and 2 over 2 will be 4. Then I integrate this one. I'm doing like u sub, but du is just 1, so I'm just seeing u squared and upping the power to be u cubed over 3, but 3 times 4 is 12. And I can keep going on from there. I'm just integrating now term by term. I'm just integrating now term by term. So it'd be a lot easier, aka it'd be possible, whereas having a power series for ln from a geo, ln is not a geo series. Well, it is, but of something that would be way too complicated for me to figure out. Just kidding, no, it's not a geo series, because that's over 1. It's not geo. Wait a minute, we're getting non-geo power series? That's a thing? I thought power series were only geo series. Nope, there are power series out there that aren't from geo series. Just geo series are the ones that we've seen thus far, but now that we're taking derivatives, all of a sudden it's not a common ratio anymore, but it's still a power series. Muy interesante. Okay, I did not open up for more questions than that. Which one? 71. 55. Where's 55? 55 gives us a function, which is kind of what we did in some of our examples in class yesterday, right? 55 gives us a function and says basically make a power series and talk about its interval of convergence. Did I miss anything? Find the geo power series, identify the interval, include the formula for the nth term. Okay. Iris, what did you see when you looked at 55? There's an x on the top. And are you comparing it to the geo? So couldn't we start with x because it's our first term? Because remember, this one is a sub 1 plus times r again, etc. Right? So what's next? What's next? And it said, please include the general term. So wait a minute, the general term. As you guys were checking the back, are they normally starting at 0 or at 1? So if we're starting at 0, then couldn't we put x times 2x to the n? If we're starting at 0, it would need to start at n. If we're starting at 1, then it would need to start at n minus 1. This wasn't odd. If you guys check in the back of the book as to, do you now know what I mean? You can know what the back of the book or what the textbook is doing based on what you see. Was it n or n minus 1? You did n minus 1 and it was okay. So maybe they're starting at 1 instead. And then, what are they asking for? Oh, interval of convergence. So then this one, you probably saw us do it yesterday, yeah? That's just between negative 1/2 and 1/2. And Kevin asked yesterday, can you do interval notation? The answer is definitely yes. Okay, but then moving on to number 71. So that one, I think we even did one. Did we do that exact example? We did one super close. The interval of 55 was negative 5 to 5? Well, no, the entire class should be backing you up right now. What is the interval for that one, guys? I bet you just looked at the wrong one, kid. Yeah, I bet you just looked at the wrong one. Then 71. All right, what'd you guys do? Integrate what? Like, who on earth is little baby f? Was there something up above?
Yeah.
Yeah. Bummer. We have to go look at him. 69 gives us x minus 1 to the n is our function f of x. So what are they wanting us to do? Sorry, Iris. I just erased the work that I had for that, or else I could show you how I could rewrite it. Because the way that I wrote it was x times 2x to the n. But couldn't we, and n minus 1 I was starting at, I believe that would have been n equals 1, right? To infinity. Another way of writing it is that we could have made that x to the 1 times 2 to the n minus 1 times x to the n minus 1. These are like terms, which means I can add the exponents. And so I can make that x to the n with 2 to the n minus 1 being within mine. Does that make sense? So all they're doing is, because this is, to be honest, this is not simplified, right? I have an x and I have an x. We should combine their exponents. So they're just combining. Let me go ahead and take a new picture then, so I can get rid of that. So then number 71. The interval that you guys had back there, I believe it was x minus 1 to the n?
That was a sequence. You have to make it a function.
Oh, okay. So it was in a series?
Yeah.
Thank you. So it was like that? Was there anything else?
Make the function first, and then.
No, I see, but did I write it correctly?
Yeah.
Thank you.
Yeah.
So then if starting at 0?
Yeah.
Okay, so it's 1 plus and then x minus 1 and then plus x minus 1 squared. Okay. So then once I have that, they're wanting me to integrate. If we were making this a function, we could put our a sub 1 over 1 minus r, which would end up being negative 1 over x.
2 minus x.
Oh, sorry. Thank you. This one, if we see it in this form, I can't see where it's centered. This one, I can see that the interval of convergence is centered around 1, which helps a little bit more and gets me to the geoseries a little bit nicer as far as just thinking. But when they want me to integrate the function, so this is my f of x right above. Huh? I do my a sub 1 over 1 minus r because it's a geoseries. So there's my a sub 1, my first term over 1 minus the formula, and then my r. That's a negative x, and then that's a positive 1. 1 plus 1 is 2. Oh, well, I haven't integrated. I was just doing number 69. I was starting with the information they gave us. Because this one says, okay, well, if this is f, I need to integrate, right? And so you could integrate term by term, but they don't care about the term by term. They just want the function. So I can just go ahead and integrate my 1 over 2 minus x dx. You do u sub. I'm going to have a negative with an ln of that 2 minus x. Yeah, I haven't gotten there, but thank you. But have I done my definite integration though?
Yeah.
Or my indefinite integration? That's what I was focusing on first?
Yeah.
Okay, good. And I didn't go to u sub, so I can go ahead and just use those x bounds, and I have that just fine. And so when I go to plug in, I'm going to go ahead and have x, my negative ln of 2 minus x, which is good. And then I have my minus and negative, which is addition. Good. Of ln of 2. Now, log properties, like we learned, well, once we get rid of those absolute values, because absolute value of 2 is 2, I have a log minus a log. And remember, when you have logs subtracting logs, I can go ahead and make that a division. Technically, I don't really need the absolute values around the 2, so I could keep them around my numerator, 2 minus x. But as you guys are looking at all your answer choices, I don't think they have this ordered the same way, right? So can I flip those around, and can I make that a negative inside the absolute value x minus 2? Pretend that's an x minus 2. And then what's the absolute value of a negative 1? Positive 1, and so it's going to end up actually being the exact same thing. Don't ask me what happens.
It should be, so when I bring in the log rule, it should be ln 2 over 2 minus c, but it's the random. You have to flip it and then take out the negative sign to match.
I took out a negative.
It should be 2 over 2 minus 2 over 2 minus x.
Okay, anything else that we need to see? Going once, going twice. For those of you for whom that was productive, you guys talking in groups, you guys watching up at the front, good. For those of you guys for whom it wasn't, maybe just ponder, and as I don't want to waste your time, maybe think about how you could have used all of that time a little more wisely, because that was quite a chunk of time. Could you have been doing your homework? Could you have been taking notes? Could you have been looking ahead in Google Classroom at the next homework? How could you have used your time well? But as we do that, I technically do have some discoveries that we would have done at the beginning of class if I hadn't been giving you a lecture, but for right now, we'll just go to section 10.2, Taylor polynomials. Because what you saw in homework was last night was that there are power series that are not geometric. They come from geometric, being derived or being integrated, but they are not geometric in their actual nature. So who are these other power series, and is there a more general way of defining them, describing them, talking about them, etc.? As we did, thank you AJ for your questions, as we did 27 and 33. They came from a geoseries being derived, from a geoseries being integrated, but they were not geoseries themselves. So who are they, and is there another way of getting them? The answer was yes, but it would have been a lot harder. If possible, to start from a geoseries, it's a lot easier to form a Taylor polynomial that way than using the formulas that you guys see up on the board. I'm going to go ahead and make this as big as possible. Section 10.2, Taylor polynomials, kind of coming from the idea of a power polynomial. A Taylor polynomial says it doesn't need to match up with a geoseries. It can be any function, and I can make a polynomial out of it. But how I make a polynomial out of it has to do with its derivatives. Taylor-Maclaurin's. Taylor is the general one. Maclaurin is the specific one. Taylor says it's centered anywhere. Maclaurin says it's centered at 0. And this was what I said the other day, and you guys had no point of reference, no context, but I mentioned something to do with MVT and roles. MVT is general. Roles has to do with when f of a equals f of b, and I can guarantee a 0 of the derivative. Kind of similar here in that Taylor is general, Maclaurin is specific, and specifically centered at 0. However, if you guys notice, these polynomials are finite. They are not going on forever. These are finite. They are not going on forever, which is why it's important to note down here that these that are finite, that don't go on forever, can only be approximations. Can only be approximations. If they can go on forever, well, depending on the interval of convergence, maybe it'd be better than an approximation. Tomorrow when we start off class, I want you guys to have your graphing calculator. I want it to be radian mode, and I want you to be ready to see another way of writing sine of x as a polynomial. But I want you to have your calculator to do it. It'll make it a bit more exciting. I know most of you don't bring calculators, but let's bring them tomorrow. Not because we need them for all-day samples, but because they'll have a cool discussion. Now, for some of you, this page is kind of like a godsend to some extent, because last night in homework, today when we were going over homework questions, the last couple of days in class, you're like, she's doing all this creative stuff, and you just kind of have to see it or else. But what do you see up on the board right now? Two formulas. Two formulas that are going to be endeavor cards with two formulas. And those formulas say, hey, instead of having to be creative, you could just figure out who's f of c, f prime of c, f double prime of c, f triple prime. Ooh, and factorials come up. I wonder how that works, and I wonder if we'll figure out where these formulas come from to some degree tomorrow. Whether it's at c or whether it's at 0, no big deal. You just have to do it instead. But is there another way to make a power series? And then we'll compare it kind of to those ones that you guys struggled with last night, and then ask ourselves the question, once we learn these, which way was better as far as getting there? And you'll understand why we started with 10.1 and we didn't start with 10.2. And remember, once again, our book is starting off its whole discussion on sequences and series. Nope, sequences, it started last chapter. But series, it was just starting its whole discussion on convergence and divergence. So, of course, it would start with the geo, because that's the one that you learned in pre-calc. Right this second, guys, off the top of my head, I don't remember if I want you to make this one endeavor card or two. I think just one, because to be honest, What's even more important than Taylor-Maclaurin polynomials are Taylor and Maclaurin series. And so those ones will have a separate endeavor card as well. But I want you to know the difference between polynomials and infinite series, because the polynomials are going to be approximates. And it's kind of nice also to have the general term, because as you guys have noticed in a lot of questions, they want you to be writing the general term. They're getting you ready for the AP in that sense. But anyway, for today, sadly, I'm pretty sure this is about as far as we can get. We could go ahead and pop over and try to make a Maclaurin, but for right now, we'll wait because I want us to do that sign discovery first before we make a Maclaurin out of sine or of sine. But yes, we are super close to saying ln, sine, cosine, all of these functions that up until this point, it's like, well, I know a few of them and I'll approximate the best I can. Is there another way of looking at them where we just have polynomials? We'll see tomorrow. Okay, so tonight, those of you guys that didn't get homework done for this morning, well, let's get it in by the end of the day for 3/4 same day credit. You can catch up tonight. The rest of you guys, you kind of get a free night. And I'll see you guys later. We have a whole nother 60 seconds. Go team to the donut. Hang out. Have fun. Check in. I'll get Dean's video loading.